Welcome to the first video in our new series called Video Standards, Signals, Formats, and Interfaces. The title is inherited from a book published 20 years ago. The video industry and its technologies have progressed significantly since then. We have new formats, new frame sizes, and even new interfaces like HDMI. We will try to provide detailed and updated explanations in a number of short clips dedicated to particular subjects. Think of these videos like a series of lectures for the online era. A video standard is a set of rules and protocols defining how a particular video system or product should behave. They're made in agreements between organizations and countries at global, regional, and national levels. Some standards bodies are global institutions like the ITU, the ISO, and the CIE. They publish and maintain well-known official international standards. More regional institutions like the EBU also issue their own technical recommendations, which are effectively international standards too. There are industry alliances, associations, and societies like the SMPTE, which started as a local professional club and grew into an international organization issuing well-known standards. Standards bodies try to cooperate rather than compete, so the documents they produce are often very similar and many are nearly identical. In the past 20 years, video frame sizes increased significantly. Total pixel counts are now 25 times greater. There is still some confusion about naming conventions, so we'll cover that. In the past 20 years, video technologies progressed in several directions. The transition from tape-based to file-based production, the development of new codecs, and the launches of new multi-screen, multi-format content delivery mechanisms. Today's world broadcast map represents a mixture of some legacy analog systems like NTSC, PAL, and CCAM, with more recent digital television systems. In a global scale, this transitional period lasts for decades, making the conversions between all these formats very important. Old-fashioned interlaced television is still with us. More than half of the world's video assets are stored in interlaced formats. Historically speaking, the most significant boundary in the world of television is between different frame rates. The world broadcast map is still split between 50 Hz and 60 Hz countries. And strictly speaking, 60 Hz is really 59.94 Hz. Global broadcast content is still delivered mainly by three major systems developed in the last century: terrestrial television, satellite television, and cable television. But the market share of internet-based delivery is growing rapidly in many countries, keeping pace with the growth of mobile video devices and social networks. Video standards consist of elements covering different facets of a video system. Levels mapping schemes define how a camera converts light into signal levels and how a display should convert video signals into light. 20 years ago, there was only one way to do it, and now we have at least 4 different ways. Color information representation has also become more complex. We have several sets of color primaries and color matrices in use today. They're called color spaces or color volumes. The same is true of aspect ratios. In addition to the classical 4:3 and 16:9 formats, systems now have to deal with a variety of letterbox, pillar box, and anamorphic formats. Scanning standards determine the number of pixels in a frame and the number of frames per second, and don't forget their accompanying interlace issues. A video format is an agreed-upon way of packaging up picture information for transmission or recording. There are many dimensions. Signal data can be RGB or YUV. It can be wrapped in a container such as MXF or sent as a live stream. There are many codecs available. Conversion between different formats, when you use a few different compression codecs in a sequence, may cause serious problems at the end of the line. Video interfaces are often understood as a physical connection, but digital interfaces also depend on protocols and several layers. The physical layer is more than just a connector shape. It includes the layout of the pins in the connector, voltages, sampling rates, signal timing, and so on. HDMI interfaces may even add a final layer of compression and re-expansion within the display itself. A cable and its familiar connector may carry different signal formats. A UHD TV signal, for example, can be transmitted over 4 SDI cable interfaces, or over one single faster SDI interface, or over 2 or more HDMI interfaces, or over one faster HDMI interface. Let's discuss this simplified television system diagram. It's oversimplified but still true. It depicts a complete television system: a light source, a scene, a camera, a connection, a display, and a happy viewer. But happy viewer is watching the screen in some particular viewing condition, including their own very important ambient illumination, which could be as high as sunlight or as low as a very dark home theater. Problems occur when serious experts pursue the ideal of the display's exact reproduction of the original scene's colors, light levels, and dynamic range. This idea conflicts with fundamental features of human vision. If you go from a dark cellar to the sunlit beach, you will be nearly blind for a few minutes, and a similarly temporary loss of vision will happen if you return to the dark cellar. Our eyes can adapt to a vast range of light levels, but it takes time. Therefore, a high dynamic range or HDR movie that mixes dark and bright scenes too quickly won't be seen correctly unless you take that time into account, scene by scene. It's more useful to think of the purpose of a television system as creating for the viewer a more or less trustworthy illusion of seeing something similar to the original scene. Just like when you look at a matrix of red, green, and blue dots, you see an illusion of nice color pictures because the pixels are very small. Television is about the illusions it can create, and a happy viewer is the only important measure of success. Today, we have at least 4 different video formats based on different dynamic range models. There's the traditional standard dynamic range model, or SDR, in which only relative brightness is important. There's the widely used log camera format, which is used only in production and post-production, but is in fact an HDR format. There's the perceptual quantizer model, or PQ, which is the foundation for 3 major HDR formats: Dolby Vision, HDR10, and HDR10+. And there's the hybrid log gamma model, which is a sort of halfway house between SDR and HDR PQ. Each HDR format has advantages and disadvantages, which we will discuss later. In all cases, HDR television can give you wonderful pictures using very sophisticated signal processing. A full transition from SDR to HDR will take many years. A lot of televisions and set-top boxes have to be replaced. To make this transition a period of peaceful coexistence, we need mixed production methods with up conversion, down conversion, and cross conversion. At an important sports event, for example, some cameras may be SDR and others HDR. The program output should be provided in both SDR and HDR formats because while the majority of the world's viewers watch on SDR displays, a significant number have already purchased HDR televisions. This example illustrates the level of sophistication needed for setting up, configuring, and checking HDR equipment and displays. Any new technology like HDR requires new tools, and the complexity of test procedures always goes in one direction, up. We'll start addressing that in the next videos. This video was prepared for you by a team of experts. Produced and narrated by Joseph Mark, a member of SMPTE's HDR committee. Written by Dr. Victor Steinberg, co-founder and president of VideoQ, technical awards winner and author of the Video Standards book. Conceived by Roderick Snell, co-founder of Snell & Wilcox and winner of several technical Emmys and Queen's Awards. Technical consulting by Maxim Levkov, author of the Video Encoding Cookbook. This video series is brought to you by VideoQ, and you can download these slides and this video from VideoQ.com. VideoQ makes products and services for all sorts of video and audio processing and quality assurance. Based in Silicon Valley with software developers and distributors in several countries. Thank you for watching.